Hello and welcome to Live from the Lab. This is the show where we talk about different technologies that Bruker has developed to help scientists understand the world around us. Today's topic, X-ray reflectometry. Now, X-ray reflectometry is a technique that's used to measure thin films. What is a film? Or a thin one, I give you? Well, a film is anything that we're applying to a surface in order to modify its properties. A classic example might even be paint on a wall. There we just want to get a little bit different cosmetic effect. But in the instance of, say, chrome on a bumper, we're actually trying to get both cosmetic and also some chemical effects, where it can become a little bit easier to keep clean. Now, modern thin films are even approaching smaller and smaller thicknesses. We're getting to the point where films can actually be just a few atomic layers thin. And in that case, what we find is that these materials do some pretty amazing things. In fact, this lays the basis for modern sensors that we find in all kinds of devices, such as our cell phones or video games or our TVs. Now, in order to learn a little bit more about X-ray reflectometry and how it can help us to understand thin films, we're going to see it in action today. We're going to do some actual refinements using DIFFRAC.XRR. That's a software that's been around, but we just had a new release of it. And actually see how we can do these refinements. So with that, let's go over and see it in action. Good morning, Jonathan.
Good morning, John. Thanks for having me on again. It's a pleasure.
Thanks for joining us. So today's topic, we're going to talk about X-ray reflectometry.
That's right. So Bruker has spent a lot of time developing software for refinements and things like that to help us determine the thickness, roughness, and density of the individual layers in our thin films that are on top of our substrate.
So let's talk a little bit about what X-ray reflectometry actually is, though. This is a type of measurement, right? Now, how do you do this measurement?
So this is essentially X-rays come in very shallow angle and they reflect off the surface, and essentially after you hit a critical angle you start to sample the buried layers underneath that top surface.
So I noticed that you said the word reflect, not necessarily diffract.
That's right. So it's technically not diffraction, although the very common diffractometers that people probably already have in their labs are well suited to do this type of measurement.
Okay, so here the beam is actually, like you said, it's going to bounce off the surface, and from that bouncing we get some different effects, and that's what tells us this information.
Exactly, yeah. And one of the nice things of not being diffraction oriented is that it'll tell you information about amorphous layers, it'll tell you information about crystalline layers, so it's atomically, structurally agnostic in that sense.
And does it only give you information about the surface, or do you get anything deeper?
So you get, actually, to pretty much hit right on that point, you do get information deeper into the surface. So from buried layers, you can get individual layer thicknesses, roughness, and density.
Okay, and what would the limits be there?
So typically we're talking about a few nanometers thin film on the surface of the substrate, all the way up to about 100 to 200 nanometers, depending on your instrument resolution.
Okay, and we'll see some actual results, but one of the big differences between, say, your classic imaging type solutions and XRR is going to be the sweet spot, right, for this measurement. It's not necessarily the thicker things, right?
Right, exactly.
So when we're talking, the sweet spot, actually 10 nanometers or so, that's really easy to measure, even 100 nanometers, but, upper limit, we're talking
probably like 200 nanometers or
200,
so.
And that's even a little bit aggressive.
Right.
We need a pretty big machine.
Yeah.
But on the thin side, I mean, I've even measured things that were just a few atomic layers thin.
That's right, yeah. So that's the beauty of this technique. So we're talking nanometer scale thin films.
Yeah. So now let's contrast a little bit with some other techniques. So
AFM's one that'll get you roughness on the top surface, but it doesn't tell you anything about the buried layers that are underneath that. If you have some kind of a super lattice or something like that, multiple thin film layers, it's not going to tell you any information about the roughness of those individual layers.
And then we've got some other things just for thickness. So, as a film grower, sometimes what we do is we take the wafer, we blanket off a side of it, deposit, and then just profilometer, right?
Yeah, that's right.
Drag a little stylus over it, you get a little step, tells you the thickness, right?
Yep.
So that was one technique.
I think ellipsometry is another one that uses light also to extract thickness. Yeah,
that's a big one in terms of the semiconductor space. Now, the big difference, I think, between ellipsometry and XRR, though, is it's fundamental. XRR is. Whereas ellipsometry, yeah, there are some models out there, but generally what people do is it's more of a correlation.
Right.
and you're looking at polarized light and things like that. But otherwise, it's actually very similar.
Yep.
I mean, bouncing the light off the surface.
Yeah, exactly. It's just reflectometry, basically. Yep.
Is there a limit on what kind of materials you can measure? Now, you mentioned you can do amorphous and things like that, but what about things like heavier, tungsten and...
Well, that's going to limit your penetration depth, basically, right?
Okay.
So, the tungsten ends up being a very good scatterer, right? So, high electron density. So that could be a limiting factor of not being able to read those deeper buried layers.
Okay, but there is no limit in terms of you need optical clarity, typical ellipsometry. Okay, so now you had mentioned the machine itself, though, and you said that we could do this on a diffractometer. What do we need on our machine in order to do this measurement?
So basically, you want to have the ability to, put a fine slit in there. If you have a fancy mirror, get your nice parallel beam optics.
But not necessarily required.
Yep, not necessarily required.
0.1 slit works really well.
Yep, exactly. And a good detector, you need it would be preferable to have high dynamic range.
Okay.
Because we're measuring over such large, like 10, it could be 8 orders of magnitude in intensity, right? High dynamic range is preferred. If you can't, then you can use a copper absorber. We're going to show an example of how you can merge data that was taken piecewise with different copper absorbers. The software does a great job.
That was always that classic approach. Was I had my little soda can detector, the scintillation counter, and that can you get linearity up to a few tens of thousands. Stick the copper absorber in, measure the low angle part. Actually 2 coppers, then 1 copper for the next part, no coppers for the low part. But now that Eiger detector has really transformed this because you can do it all at once. So
exactly, makes life easy.
Yeah, that's great, but not necessary. Right, just like the mirror. Not necessary, just makes the measurement a little bit better, right?
Yep, exactly.
And then sample stage-wise, we just really need to be able to accurately set the height.
Yep, so you can use the X-ray beam to set the height of the sample, and then you align the detector to the specular reflection. And then, some anti-scatter optics, obviously, like a knife edge, would be preferred too.
Okay. So now that we've got that, we would do the measurement. The measurement is just a simple, like you said, there's a little alignment, and then you do a coupled scan, but we get the measurement. Now what do we do with it?
Well, if we have good data, we can then analyze that data using our software that Bruker's been developing.
All right, great. So DIFFRAC.XRR, that's the software. And we're going to see it in action here, right? So
let's take a look.
See what it looks like.
So here, I'm going to pull in some data. In this case, we're looking at a platinum thin film on silicon.
Okay, and one thing I wanted to mention is that the scans that we're going to be looking at today, they are available in the tutorial file. So if you do have the software, you want to do some of these steps, go ahead, just go into the tutorial files there. You're under program data. So it's like C program data. And then tutorial, Bruker AXS tutorials.
Yep.
XRR.
If you right click in the start menu and say open file location, it'll be right there.
There you go.
Yeah. So, all right, so very easy to load in the data. We just kind of open it using I think it'll import raw files. It'll do the Bruker proprietary files as well.
Okay.
So you can see here's what a typical XRR curve looks like, right? So again, you can see we're starting very low 2 theta, going out in this case to about 10 degrees 2 theta, right? So shallow angle.
Okay, and that's actually pretty exceptional, right? To be able to get out that far.
It is actually, yeah. So normally, if the signal can decay pretty rapidly, so that's good to see.
Okay.
So one of the things that I mentioned again is we're plotting this in log scale because we're going over so many orders of magnitude of intensity. It's easier to visualize the information this way.
How long would a scan like this take?
Could take a few minutes. Could take an hour, depending on the application. If you're looking at very complex structures like superlattices, where you need the resolution, so you got to use a fine slit, or something like a Pathfinder plus analyzer crystal. Then you might have to count a little bit longer. So you're basically, it depends on the situation.
Sure. Yeah. Okay, everything from like 10 minutes, something really simple, all the way up to a few hours.
Yep, exactly.
Okay.
Yeah. So you can see in this case, we have this kind of plateau region here at very low angles. So we get this direct beam. Then we approach what's called critical external, or total external reflection, sorry. Basically meaning that near 100% of the X-rays are reflected off of the surface of our sample.
Okay, and I notice that we have this kind of like going up, and I know that sometimes people see that feature, this going up at very low angle. What's that coming from?
That's coming from a combination of sample size and beam size, right?
Ah, okay. So at very, very low angle, that beam, it really spreads out, right? And the sample is only finitely thick, and then as we go up and up and up, you get more and more and more intensity, right?
Exactly.
Until everything, and that's the plateau.
Yep, you got it.
All right.
So you can see as we start to hit this critical edge region,
yes.
Now our X-rays are penetrating into our sample, and we're going to start to get information about those buried layers and interfaces. And this is basically defined by the top layer density. So we can extract some density information from this data, which is very interesting. We'll show modeling on how to do that.
Okay.
So essentially, we get these reflection fringes as our X-rays penetrate into our sample. So this is basically interference from each reflected wave off of the interfaces.
Okay, so we get the beam is coming in, that's that first drop feature, right? The beam actually starts penetrating the sample, so we lose intensity coming off.
Yep.
But then the beam that's now penetrated hits the next interface.
Yep.
And then that's going to give us signal.
Exactly.
And when we see that interference pattern, so that means we can get constructive interference where we see it go back up and then down depending on the thickness. Right?
Yeah, you nailed it.
Okay.
And what's useful is the spacing between these fringes can be used to quantify thickness of our layers.
Okay.
It can be the amplitude of the oscillations can be used to determine the density differences between our layers.
Okay.
And the decay in signal is determined by overall signal, and also of the oscillations is determined by the roughness of the interfaces of those layers.
All right, and the analogy I like to use here is, say that we're sitting out on the lake. You know, here it's Wisconsin, it's kind of that fall season right now, so we get these beautiful sunsets, and sometimes you're sitting out by the lake and you see the sun coming down, and if the lake is nice and still, then you get really high fidelity, you get a lot of light coming off of that surface. That's going to be a smooth surface. So you're going to get that signal going over a long area. On the other hand, if the lake is a little bit rough that day and kind of wavy, like a rough sample surface, you get a lot more diffuse scatter, and so that intensity is going to decay much faster.
Yeah, that's right. So every roughness of the sample is going to take intensity away from the specular reflection and scatter it off specular, what we call diffuse scatter, right?
Yep. So, and one other thing I wanted to note here was that the critical edge, so that initial drop, that's actually important too, right?
Yeah, so that's basically going to determine the density, or the density determines the critical edge there. Yeah.
Okay, so that's the density of the top layer.
That's correct. Yeah.
Okay.
Yeah.
All right.
Yeah.
So now that we've got this really nice scan, we see some wiggles, stuff like that. What do we do with it? So
one really easy tool that we can use, and that's built right into our software, is taking a Fourier transform, because we do have a periodic oscillation in our pattern. And that's going to give us a rough idea of what our thickness is of our film. And again, we know based on the processing parameters that it should be around 10 nanometers, right?
Okay.
So I'm just going to go ahead and we'll click Fourier transform, and you can see, I'm going to make this a little bit bigger. You can see that we get a peak in the Fourier transform that correlates to roughly 9.7 nanometers.
So don't we have to put any other info in here? Don't we have to type in a model?
No,
or?
There's no. This is a modelless.
Really?
Yeah.
Okay.
Calculation. Yeah.
Yeah. I mean, in the past, I guess the way I used to do this before programs like XRR was bring it into Excel, plot it out, find the maxima, and try to calculate what the mean separation is, calculate out. But here, all you have to do is just press a button.
That's it. Bruker's taking care of the work for you.
Oh, wow.
Yeah.
Wow.
So now we can go ahead and take some of this information. This is kind of where I like to start when I do my analysis.
Yeah.
We can take this information, and that'll help give us a baseline for when we do modeling and refinement of this data. And when we do that, we'll be able to get a complete picture of our thin film.
Mm-hmm. Now, would this only tell you the one frequency? What happens if I have two layers?
Then you would see two peaks in the Fourier transform, or three correlating to the addition of those two, thicknesses.
Yeah, three, because you would have the thickness of layer 1, the thickness of layer 2, and then the thickness layer 1 plus 2.
That's right.
Right?
Yeah.
Okay.
Yeah. So we'll see that in later examples too.
Yeah.
So if we have time.
Yeah.
So what I'm going to do now is basically build a sample model. And we're just going to do this from scratch since it's pretty simple. We just have one layer. It's not like we're building a super lattice or anything like that. So our bottom layer is silicon. So you can see we have a database. You can import crystal information files if you want to add to this. You can build them from scratch.
Okay.
It's been made very easy to do so. And we're going to put our platinum on top, PT. And then we're going to change the thickness of that platinum to, let's go 9. Let's go with what the Fourier transform told us, 9.7 nanometers. And so you can see kind of a plot of density versus thickness here. And one thing that we could do if we were, being very critical of ourselves here is we can change the modeling of this interface here away from error functions to different types of models. Depending on the roughness, it'll create a density gradient going from one layer to the other. So let me just show you what that looks like really quick. So if I just change the roughness here, let's go a little bit smaller so we can see the boundaries.
Okay.
Yeah, there you go. You can kind of see that now. Actually, if I do this and re-zoom, you'll be able to see it even better. Yeah, so there you go. So now we have kind of a density gradient going from one layer to the next, and you can play around with these interface parameters to get you kind of see how the density gradient changes with the different models.
Yeah,
right?
and so you're mentioning density. So density is kind of the simple way to think about this in terms of scattering. I mean, X-rays scatter off of something based on their electron density. And there's other characteristics in there too, though, things like absorption and such like that. So that's why it's important, you had noted, when you bring a material in, you want to bring in the CIF file, that's the CIF, or you can bring in a structure file from something like an ICD database or the COD database, that get CIF, but it brings in the atoms too. And so that'll help to refine that even further.
Exactly, yeah, that'll give you the most complete information. So now, if I go ahead and take this sample model that I've put together, I can actually produce a simulation of what this pattern would look like, roughly, in an experiment.
Okay.
So you can kind of see it looks very similar. It's only going out to about 5 degrees 2 theta here, so it's a little bit more compressed relative to the other one. So you can kind of see pretty similar features if we look at it out to 5 nanometers, or at 5.2 theta, excuse me.
So this is kind of annoying, though, that I have to click back and forth and back and forth.
Well,
is that really what we have to do?
The beauty of this is that we don't have to do that. We can actually go ahead, use our simulation and modeling to fit and refine the experimental to the experimental data. So we're going to do that now. If I go ahead and right-click and then create XRR fit of our experimental data, it's going to populate again in our evaluation section.
Oh, wow.
And you can actually see it aligns quite well to the model, especially this critical edge here.
And one thing I like, too, here is how the software automatically brought in the line, so the simulation being a line.
Yep.
And then the data points are actually little x's. Yeah. So that really helps to kind of visualize that differential between the two.
Yep, exactly.
Okay.
So now we kind of have to play around with the different parameters. You know, we know that we have some roughness because we see some decay in the signal. Right, relative to our simulation. So we can go ahead and change the roughness parameters. Let's try like 0.2 and see what happens. Okay, so that's going to change the overall signal. If we change this to like 0.1, you can kind of see how that changes, right? And one thing to note too, when we talk about roughness, is that there can be physical roughness. So that is the surface itself has, or the interfaces have a physical roughness. But here it's more about density roughness. So if you have interdiffusion. Right, like a gradient, a density gradient. Yeah, that can also be seen as roughness. Yep. So exactly. So we have our thickness of our layer. I'm not going to change the density right now. Okay. I'm just going to stick with my thickness. I'm going to stick with my roughness. Actually, the first step is if we go over to our instrument panel here, there's several things that we can modulate. Yes. We can change the instrument resolution, although I don't think it's necessary in this case since we're not really being restricted in that sense with this type of a sample. So we can change our background. You can see these are already set to refine. What I like to do first is go up here, try to change the conditions of our sample and our beam size to try to match the scaling here first. And then we can refine the background, and then we can kind of fix those, and I like to let the data refine based on the least squares methods.
Yeah, anytime you do a refinement, whether it's this software or Rietveld refining and Topaz and that, it's always good to try to start with some fixed values of things that you know. So if you know the beam size, if you know the physical size of the sample, if you know the resolution, just fix them. The way I like to think about it is, error space. Imagine say if we have two variables that we're changing. It's kind of like having a trampoline. It's like having that nice flat plane. We have one variable on one axis, you have another variable on the other axis. And now the errors, or the solutions, I should say, they're kind of like sticking the bowling ball on the trampoline. So it's going to kind of go down. We're going to get the best fit, the lowest error at certain locations. But unfortunately, as we add different variables in, that can create some solutions that are, they do have a minimum, but they're not the global minimum. They're not the best solution. So we do have to be careful. You turn on too many things, you're going to get more of those possible local minima, and that's going to be a solution that is kind of a niche thing, but not the right solution. So start with some fixed solutions, and then you're going to be better off.
Yeah, 100%. And you have to kind of think about what's going to be realistic.
Yeah.
Yeah. So.
Yep.
All right. So I think I've captured the background pretty well. I'm going to let that refine a little bit.
Okay.
I think we've captured the critical edge here and kind of our sample parameters pretty well.
Yes.
So now it's really all about changing our thickness, which we're going to let refine, and our roughness to try to match the experimental data.
Okay.
So what I'm going to do is not let this refine from 0 to 100. You can set limits, and there's a button right here that'll let you set reasonable limits or boundaries on these refining parameters so that you don't have a runaway fit on you, right? And if you do, by accident, do that, you can easily go edit and undo.
Okay.
So that's one nice thing about the software that I love that they built in, because I find myself using it quite a bit.
Well, sometimes you try something and it goes off the rails.
Yep. All right, so we're going to set that to refine.
Okay.
I'm not going to refine the roughness. I'm going to do the thickness first. And we could start with, you have a number of different algorithms to choose from.
Okay.
So you have extended genetic or quasi-Newton, which are, again, as you were talking about, those local and global minimum, right? So these will be good to get you to those global minima, and then simplex and Levenberg are good to get you the local minima, right? So it kind of walks you slowly to the answer.
Yeah, the way I like to think about it is that the first two methods, that Levenberg method and the simplex method, what they do is they take your current state. So again, imagine being on that plane with two variables, and you have these local minima and then the global. Is that the simplex and Levenberg, what they're going to do is take your current location on that error space, and it's going to try to refine that. It's going to find that lowest error relative to that starting point. So it's very localized. If you're in a local minima, this is just going to make that fit better, but on the wrong answer, unfortunately. But that being said, if you are in the global minima, this is very efficient at getting you that right solution. This is really going to give you the best kind of finish, the best data there. The genetic algorithm, the quasi-Newton method, what they're really good for is when you're starting out. And what they're going to do is the genetic algorithm takes the current state, and then it spawns a whole bunch of solutions off of that state in all of the variable space. And so this is really sampling that entirety of variable space, as it's going to give you the best chance at finding the global minima. So generally, I start with, say, the extended genetic or the quasi-Newton solution to start with. Then, once we start seeing it really dial in, change over simplex, a little bit more aggressive, the Levenberg method, a little less aggressive, and that's going to get you in.
Yep, and you can go ahead actually and change these parameters. I've had pretty good luck with defaults, but if you really if you want to go crazy, we give you that capability. So since I'm just looking at thickness, I'm going to, and we have a good idea based on the FFT, I'm just going to go ahead and run a simplex refinement on that, and we'll see what we get. So you can see it's doing its thing.
So since you're only allowing thickness, I did see kind of the red line moved a little bit. It's definitely better in alignment now.
Yeah, and you can see the actual value changes.
Okay. And in the top, we can see the chi-squared. That's your indication of how good the fit is. The lower that value gets, the better.
Let's wait for this thing to think. Let's see if I can pause it for a second, since we kind of have a good idea of what thickness we're shooting for. Now I'm going to go ahead and throw roughness in. And typically, depending on what you're looking at here, I can see the signals decaying. So I'm going to give it from 0 to 1 nanometer roughness. And we're going to set that to refine.
And in the table, you can also notice how the table gets a red line around it, if that's a refine.
All right, so now we're going to go for, let's try the genetic.
Okay.
And hit go. Wow.
Oh, wow.
Look at that.
That was quick.
Yeah, not bad at all, right?
I think we found the...
I think this is probably a decent refinement, yeah.
Yes.
We see it's still going, though. So let's see. Yeah, you could definitely see it honed in the roughness and the thickness, which seems to be like roughly, what, half a nanometer here for the substrate layer interface, and then the top surface.
So what's kind of neat here is, you know, you were able to fit this without changing the density, because, you know, platinum, as long as it's 100% dense film, which, I mean, you do have to think about that. Yeah. You're going to get about the right density.
Yeah, so that's a great point. You know, sometimes it definitely helps to know what your deposition process is. Do I expect to have porosity in my films, things like that, right? So,
yeah, or if you, but then if you do have something like SIGI, where it could vary the density, and then the density is actually linked to the composition, you can actually refine on that too. So that's another thing that you can do. So this looks like a really phenomenal fit.
Yeah, not bad at all, right?
Yeah.
So you can see the chi-squared value looks reasonable. If we were to then, let's say, just hit simplex for fun, if it gets it any better. Nope, so it's happy.
Okay.
Yeah.
Now, one other feature I do like, here in this case, we don't necessarily need to use it right now, is ranges, though.
Yes, yeah, so that's actually a very good point. We can actually define ranges in our curve. If there's areas where we're not necessarily happy with the way that it fit that area, maybe there's something that we're missing that we want it to really focus on.
Yeah, say like this area right there in the middle around 4.
Yep, where you can kind of see the red line is coming off the blue a little bit.
Yep.
We can go ahead, select that region, give it a little weight. So let's say, I don't know, we'll try 2. And then go ahead and click run again. You can see that it tries to squeeze that refinement a little bit. It's giving more consideration to that region.
All right, so it still is looking at the other regions. Yep. Anything that's not in that range is a 1 weight, but then here it's giving, you know, twice as much kind of thought to. And you can do this with multiple ranges.
Yep, that's right. So you can see it kind of fell off a little bit over here.
Yeah, we
so
fell
let's
down
go ahead
there.
and throw a range for that. That looks pretty good. And we could give this a weight of, I don't know, let's say 2 or 3. Let's try 3.
Yeah, there we go.
There you go.
So, but you can definitely see that balancing, and this could be something like just a little oxide layer around the silicon, and you can always play with that. You can try to refine this more. One thing to think about, though, is the topic of over-refinement.
Right, yeah. You can fit anything. Like, you can make the software fit anything you want using almost any parameters you want, right? So it's a matter of what's realistic, though.
Yeah. Every good refinement starts at the measurement. You can't get a good value out if you don't have good initial data. So, I mean, yes, you can fit it, you can make it, oh yeah, look at that, it's fit, but is it real? I don't know. So think about that, garbage in, garbage out. Yeah. You want to have good data to get good results.
Yep, couldn't agree more.
So, okay, so this looks great. Now, what if we wanted to get, say, like a report out? What if I wanted to see the result? Do I have to just take screenshots, or how do I do that?
So if you wanted to export the data, you can very easily do that. If you go ahead here on our solution tree, where we have kind of this data tree, and you can right-click it, and it'll go ahead, it'll export the scan data. It'll actually export the FFT as well. Okay. If you wanted to plot that using some third-party software. Yeah. Yeah, so that's great. We do also have our own project builder. So it'll actually export the curves for you in a nice project format. It'll export the FFT. It'll export pretty much the fit parameters that we've refined, right? Okay. So this can be very useful. It'll actually export the sample model into a nice report format.
So if you're doing a lot of standard measurements kind of over and over again, you can just make a nice report format and be good there. And you can also do some other things to help you, right? Like samples and stuff like that.
That's right. So you can actually, so in the next few examples, we'll actually import samples that were already predefined that you can save in the software. Another thing that we have the ability to do is create workflows and things like that too.
Okay, so let's go ahead and, you said another example, let's try it out.
So what I'm going to do is just X out of the project view here. We'll go back and what I'm going to do is just start with a clean slate here. So I'm just going to click clean solution. We're not going to save it because I know that data back and forth now. You know, we know we kind of have a good idea, so I can always come back and rerun it.
Yeah, but you could save it.
Yeah.
If you want it.
Yes. So I'm going to go ahead, import. Let's try the 3 layers example. So you can see
a lot more going on.
A lot more going on, yeah. So you can see we kind of have our typical critical edge here, and you can see there's a lot more happening with these oscillations because we have multiple layers now.
Okay.
So again, we start with our FFT. There you go. Look at that. So it automatically tries to pick the range that'll be best suited to get you the best FFT, right?
So now, so I guess you said 3 layers, right?
Yes.
And I'm seeing like a little oscillation, I'm seeing a big oscillation. But the interesting thing is here, we got a lot more peaks in that FFT.
That's right. So you have to also take into consideration the addition of the thickness of 2 or 3 layers. That's going to pop up here.
Okay, so what do we have roughly here?
So, and this is a carbon-nickel-carbon layer on silicon, by the way.
And what are the approximate thicknesses? What were you thinking?
So the approximate thicknesses, I actually don't
It kind of looks like
but our FFT is telling us, roughly, we're seeing multiple peaks here at low.
Yeah, it almost looks like 3,
low
5, and then we get 8 because 3 plus 5 is 8.
There you go. Yeah.
Okay, and then we have this 55, which can't be devised really by the others. But then 64 is simply
plus 8.
56 plus 8. There we go. Okay, so that's where it's all coming from.
So we know we have 3 layers, and then we can kind of, based on our FFT, break it up based on that.
And what really amazes me is how that tool, it didn't require anything. It didn't require any information. It does have the wavelength that comes in the file.
Right.
But other than that, bam, you just get out the answer. So
the thicknesses roughly of each layer I have saved in the solution, in the actual sample file that we're going to now import into our model.
All right, let's bring that in.
And we'll see how it compares. So if we go ahead to sample here, we go ahead and load sample. So you can see we have the 3 layers, carbon, nickel, carbon on silicon.
Okay.
So we're going to go ahead and import that. We're not going to save the vacuum sample.
And this is really nice if you're doing the same sample over and over again, or you just have a basic template that you're starting with. Now you could go and you could edit it slightly.
Exactly. Yep. So you can see it pulled in the sample pretty easily, and you can kind of see density as a function of thickness again. We're going to go ahead and I say let's just go right to the refinement.
Okay.
Since we have starting values already.
You're the expert.
Let's see what happens.
Let's see what happens. It's either going to be amazing or it's going to be
So we're going to go ahead and select create XRR.
We're going to see a struggle and sweat.
Let's see. You never know. Sometimes that's what it takes. Oh, that's actually a pretty good starting point.
Yeah. I mean, I'm seeing the oscillations, and then I'm kind of seeing, what I'm missing is kind of that 3 and the 5. But I guess that's a good starting point. This hasn't even refined yet.
Yeah, that's right. So I'm just going to turn on a bunch of parameters here. We'll go ahead and pick reasonable boundaries for each of those thicknesses. And we'll also do the same for roughness. Density I'm going to keep fixed, as I normally do. Let me not forget to do that. Let me just double check here. There we go. Go back to roughness. Okay, let's do, I think I'm going to switch this over to 0 though.
Yeah, while you're filling that out, one thing I like to do with density is look at that critical edge. And if, your top layer, if it's really off, the critical edge is really off, you either have to have a really good reason for that, or when you scanned, you probably have an offset in there. So you'd have to offset the data to try to get some results out.
That's right. All right, so we're going to refine that. Let's refine this. Before I do refinement, I'm going to try to get the scaling and the sample model a little bit tighter on that by that critical edge there.
All right.
Okay, let me just click that. We'll do 0 as our bottom boundary because I like no roughness. Okay, that looks good. So now we're going to go over to our instrument. I'm going to take a look up here. And now I can change our sample size. That looks pretty good, about half of what it was initially. Scaling is spot on, I think.
Okay.
I'm just going to not refine those for now. If we have to, we can always turn those on. Background, probably not 0. It's pretty close, though. I might just let that refine. Let's see what the boundaries are. Yeah, that's reasonable. All right, so let's see what we get if we start with the genetic.
Okay.
So let me just see what we got. All right, so we're refining all these parameters. Let me just make sure that one's turned on. Yeah. Okay. And we're going to hit go. Let's see. All right, so you can see where these yellow boxes are. We're hitting those boundary regions. So we might have to give it a little bit more flexibility.
Yep. Yeah, it's like it was going the right direction, and then it was like, well, hit the boundary.
Exactly.
Right? Okay.
So I'm just going to let that finish. And then we can readjust.
And we are getting a little bit longer here in terms of the show. So if if you don't have time to watch the rest of it, you can always come back to the YouTube channel here and you can watch the rest of it. And if you do have questions, in the after time, you can always send them in to our email. That email is live.events@brooker.com. But since I think this is such good information, we're just going to keep going on with this example, and then we have one more example, and then we're going to get to your questions. So looks like here we're coming down to that fit.
Yep.
So you can really see it kind of walking in.
Yeah, you definitely can. Even over here in this region, it's just a little bit offset.
And this is the thing about the genetic algorithm, is that the time it takes to find the solution is actually determined by the number of variables that you're using and then the settings in the genetic algorithm. Yeah. Because it takes its current state and then it recalculates based on the variable space and the number of different children. That's kind of in genetic algorithm, you have the current state and then you have the child states right after that. So that's why that one sometimes takes a little bit longer. But you can go in, edit the settings, make it go faster.
That's right, yeah. So one cool thing that I like about this software is you don't have to go to every parameter that I hit a boundary on and adjust those separately. You can do it all automatically just by hitting adjust limits. It's going to go ahead and create intelligent boundaries for you. So we're going to do that. It's going to reset those boxes.
Oh, okay. So you don't have to go into the individual ones and change the limits.
Yeah.
Okay.
So it saves you a little bit of time.
Yep.
There's also another option here where you can auto adjust every optimization.
Okay.
So let's go ahead. I'm going to stick with genetic. Let's see what we get.
And I do see, though, that it is in a better state, and it's approaching a better state, although we still are hitting a few limits.
Yep.
Not nearly as many as what we did before.
Yep. So we're getting closer to the answer, I think.
Yeah.
Yeah, so you can see it kind of pull that in a little bit better.
Yeah. But we do still have a yellow, which means that we're
let's go ahead and readjust.
Not yet in the perfect state.
And then we're going to go ahead and run that one more time.
And another thing to note is that right now we're just doing the genetic algorithm, so it is still the rough fit.
Yeah.
Right? We're going to do a simplex or a Levenberg in order to really bring it in.
Let's see. So you can see I kind of lost that a little bit, right?
Yes.
So what I'm going to do is create bigger roughness boundaries, and I can add a range there.
Okay.
That'll help us fit that region.
Yeah, that's another tool we got there.
So let's try that. And you can see, well, I think that's probably good right there. We'll give that a little weight to it. I think 2 is probably okay to start. And again, if you're not happy with the calculations that it just ran, you can always undo it.
Yeah.
So that's always nice. So let's go ahead, and you can see that there's definitely some roughness to this sample.
Yeah.
So I'm going to kind of let this float a little bit more. Let's go like 0 to 2 on each of these. I still can't believe you could do all this with a laptop.
Yeah. And the speed, even here, when we think about the number of things that you're refining, it's pretty amazing.
Okay. All right, let's hit go and see what we get. It's coming in a little bit more.
Yeah, it is. Yeah. And here we might even change over to like the simplex method, right?
If we think we're close to kind of that, that region, then yes, we can just kind of walk over now. Let's see if we try that.
Yeah, and you can see in the chi-squared too how it's getting better.
Yeah,
so
exactly.
Yeah. So it's definitely one of those, though. You can see that we're pretty close to the fit here. Yep. So you would just kind of continue to adjust your model slightly. Sometimes at this point you might even say, hey, you know what? I might have an oxide layer. I might have something that I'm unanticipating in there, and try to adjust it. And I think you have one more example, though. Something that's...
Yeah, a little bit more exciting.
Yeah,
we saved the best for last, the hard stuff.
So we went from 1 layer to 3 layers, and now we're going to go to...
a super lattice.
Super lattice. So
I'm going to go ahead and just pause this, and then we could clean our solution here.
Yep.
And then we'll bring in the exciting sample. And I'm not going to build this from scratch, obviously, right? So to save a little bit of time, we are just going to import the sample model for that. So you can see we have this super lattice, 10 bilayers. And this was data that was taken over using different copper absorbers, right? So I guess they didn't have a rotary absorber, or they don't have the high dynamic range of the Eiger.
Okay.
So you can see that this data was taken piecewise, right? So at near the critical edge, you have the highest intensity. You probably got to put a copper absorber in, right? Yeah. So software is very easy to merge this type of data. Let me just click out of here because I don't want to highlight project. And then we're going to highlight all of these and go ahead and merge scans.
Oh, wow.
And there you go.
Well, that was simple.
Yep, makes it nice and easy. So you can see these, you have different fringes here, different oscillations. The fine ones are due to the full thickness of the super lattice, right?
Okay. But then these really strong peaks, those are actually super lattice peaks, right?
Exactly.
Okay.
Yep. So let's go ahead and pull in our sample model. So we're going to load sample, and you can see we have the SL10X. It's carbon on tungsten disilicide.
Okay.
And that's on top of a silicon substrate. And so there you go. It pulls in the super lattice information. We have parameters. Let's just try and fit it using the fit tool. And so you can kind of see it's a little bit off, right?
Yes.
A little bit out here.
Now I noticed that you said that this is a super lattice. There's a lot of layers, but I only see like 2 layers on a substrate. Yeah,
great point. So if we expand, we can actually expand this if we go ahead and show you that all we've done is basically repeated. So you can see repetition of these two layers, basically 10x.
Yeah.
Right. So let's go ahead and I'm going to go ahead and refine thickness. I'm going to go ahead and refine roughness as well. Should I just do like Hail Mary?
I mean all the thickness and roughnesses?
Let's do it.
Oh.
We can always hit undo.
I guess we'll see. Yeah, yeah, we got some questions, so let's try it. Let's see what happens, and then we'll get to these questions.
Sounds good. Actually, you know what? I'm going to go for this. I'll do 0 to 1. I always like to have more generous roughness boundaries. Okay, we'll refine that. Again, just check the scaling of the data. That looks okay. Yep. You can choose to refine this. I'm going to hold off on that for now. Background, I'm going to have to bring that up a little bit. Look at that. Nice. Okay. Good guess.
Yep.
And we can refine that as well. Yeah. All right, so let's go ahead. We'll go with our genetic and hit play and see what we get. So you can see we're already hitting.
Oh, wow. Yeah, like immediately. It was like, whoop.
Yeah.
Let's just fit.
And I'm going to make this a little bit bigger for our viewers, actually, because we don't need. Thankfully, it compiles all those layers into two.
Oh my
so
gosh,
if you really wanted to get a better fit than this, you could actually expand and fit each superlattice layer separately.
Yeah, and that's likely some of these things that we're going to see here, like that. The falling off not being as quick.
Exactly.
It's just due to the layers being slightly different.
Yep. So that's pretty solid. Lastly, when we're looking at superlattices, I would say what we want to be conscious of is instrument resolution.
Okay.
Right, especially when we're looking at a superlattice that, can go up to like 100, 200, where we start to hit that, am I going to be able to measure this, scenario?
Yeah, the thicker it is, the closer the fringes get, so resolution of the instrument becomes very important.
And so if you take a look at the instrument panel here, we can see that we have an instrument resolution section. And so let's just take a look at this for a minute. So if I change the dot view, this is one case where I would want to do that from the actual experimental data. If I change over that to lines, I just want to see what the amplitude looks like.
Okay.
There you go. So you can see there's a little bit of a difference there.
Yeah.
This could be an instrumental resolution effect. So if I change this to, I don't know, like 0.005, you can see how that
that really brought it
right?
in. Yep.
So that's another refinement you can do when you're looking at superlattices.
And that technically the instrument resolution will either come from the slit sizes that you're using, or it comes from using a monochromator. So.
Yep, exactly. So let's go ahead and see what we get there. I mean, you could play around with this all day.
Yeah, and this one, I think you'd really have to expand that as the next step. So with that, though, I think let's get to some of these questions that we have. The first one I actually want to get to is one that had come in before. So Stanley is asking, what if I want to measure multiple points on a sample, like a large wafer?
That's a great question. So we actually just built in the newest version of the software a module that'll allow you to essentially look at different points on a wafer, let's say. So wafer mapping, that's a feature now in the software.
Yeah, and it'll actually give you a map of it. There's a great example of it. If you look on the website for DIFFRAC.XRR, you'll see a great example. One thing to note is that, remember, at XRR we're coming at a very low angle, so the beam is spread very far in the one direction. If you want to narrow that down, you can use a knife edge or even a focusing mirror, but still you're going to get the best resolution actually stepping in the other direction, in the Y direction. Another question now here, coming from Quang Ho. Which one is better for thin films between the XET and the Eiger 2R500, and how much better?
That's a great question. I am a big Eiger fan because, again, it has that high dynamic range, where you're looking at 8 orders of magnitude in intensity, so it makes it a lot easier to capture a scan in one frame.
That's right. Yeah. The Eiger, I mean, that dynamic range, like you said, indispensable with films, because substrate signals, whether you're doing XRR, you're doing regular diffraction, you're talking millions of counts per second. And then films, what, a few thousand counts per second? But then fringes, they can be a few counts per second.
Very true.
So dynamic range is king. The other thing with films, we often have a monochromator on there. So the fact that the XET has that better energy resolution for beta, that's out. Now, if you're looking at some of these new exotic materials, like they have a lot of iron,
like
transition
fluorescence
metals
and stuff like that, you have to worry about maybe.
Yeah, that might help you out with a little bit better background, but I don't know. I think I'd lean towards an Eiger.
That's probably what I would go with. Yeah.
The other thing, and we'll talk about this in a future live from the lab, is reciprocal space mapping. And man, that Eiger, it's so big.
That's right.
Woo, all of reciprocal space belongs to you.
Basically, you have total control.
That's right. Then another question, also from Quang Hao. How much thickness can measure it in 3 kilowatt and 6 kilowatt?
So sources for 3 and 6
So I think,
kilowatts.
we're thinking about if we had the generator that's a 3 kilowatt generator, or a higher, like a rotating anode at 6 kilowatts, what effect does that have on thickness?
So thickness is kind of defined by more or less the instrument resolution. So as we get thicker and thicker films, our peaks get closer and closer together.
Yep.
So that's, yeah.
So the power, 3 and 6, that's going to give you more
Intensity.
More
Right.
signal, so you'll get it in a shorter period of time.
Yeah.
Not necessarily going to help you with the resolution, though.
Yeah.
So the resolution, you're going to need a mirror. That's the next step up from slits.
Yep.
Monochrometer,
Those
that
are the
could be a
next
step
step.
up from that. And
Yep.
you can even try using an analyzer crystal on the secondary side to get even thicker. Top end,
Yeah.
man, I
Yeah,
don't
it's
know.
tou-
I
it's
mean,
tough.
1 micron, I don't think you're going to hit a micron,
Yeah.
to tell you the truth. You're going to try really hard. You might be able to see the fringes. You might be able to fit some of it.
Yeah.
Sweet spot, 10 to 100.
That's what I would say, yeah, generally.
10 to
Yeah.
100. Reasonable, 200 to 400.
That's why I kind of
High
say
end.
like up to 200, because sometimes you can get there depending on what your instrument you have and
Yeah.
what your optics are and all that.
Yeah. But yeah, the higher end generator, like 6 kilowatt,
Yeah.
is definitely going to give you a faster data, probably about
Yeah.
2 to 4 times faster. But that being said, I've also done this on a microfocus, which is sitting at
What is it, 50 watts or something?
50
The
watts.
light bulb?
Yep,
Or
yep,
the old,
but
not even the new light, the old light bulbs.
that's right,
Yeah.
that's right. And one of the benefits there, since you're hitting a smaller area in the sample, sometimes you get cleaner results because you have less variation in the
Yeah.
thickness. From Victoria, we have a question. Are there limits for the sample size? For example, does the size affect anything other than reflected intensity?
I mean, the beam spreads out at low angles, so I mean, you might have some trouble with big samples aligning it. So you just pick a higher 2 theta omega,
Yeah.
coupled angle when you align the specular reflection. But it should be fine. You can map on big samples too, right? That was
Yep.
one of the things that we talked about. So
Yeah, and you can measure, so I guess in terms of overall sample size, small, well, you know what? Yeah, you're fine.
Yeah.
What's going to really affect you is going to be that plateau in the beginning,
Right.
right? Tiny samples, sometimes you don't even get a plateau, and that gets a little shifty for
Yeah.
fitting the critical edge.
Yeah, exactly.
You got to see a plateau if you really want to fit the critical edge. That being said, on the big size, where I've run into issue has been wafer bowing.
Yeah.
If you have if you have a proper wafer chuck, you stick a 300 millimeter on there, wafer, you're okay. But if that wafer bows at all, man, that can really affect the signal.
Yeah, exactly.
The other thing to think about is if you have any suctioning. So there's 2 types of wafer chucks you can get. One is kind of flat and it has little holes. The other one has just distinct spots. If you look at the surface very carefully and you see any divots from the sucking, that can also cause some issues.
Yeah, flatness is very important.
Yeah, flatness is of paramount importance here. So, be thoughtful of that too. But yeah, overall, actually, bigger is better.
Yeah. Yeah.
To
I would
me,
generally-
ideal is like a 3-inch wafer.
Yep.
That's beautiful.
More signal.
Yeah, but a centimeter by centimeter works. I've even done 2 millimeter by 2 millimeter, no
Yeah.
problem. Another question from Victoria. How does sample non-uniformity, that is variable thickness or islands, affect the results? Would the modeled results be an average thickness or come up as a different error?
That's a great question. I would say that you're probably going to be sampling that depending on how big your beam is, right? So it probably would be an average if you're sampling all of that, right? It might also show up as more roughness if there's a lot of non-uniformities and things, right? We talked about these density gradients going across an interface, right? So you probably have more of those types of effects in those experiments. But if you were able to get your beam size down, like with a microfocus, let's say, and focus on a small area, then maybe you'd have a better shot at getting location-specific information.
Yeah, and I think that's, you really hit the nail on the head there, is that it's a variation in the roughness.
Yep.
Over the lateral area, you're getting a variation in density, and therefore that's seen as a roughness.
Exactly.
So you're going to see that signal decay a little bit faster. Now, if they're really big islands, you might get to the point that the roughness is so large that it doesn't affect it as much. So
Right.
You kind of have to play with it, and you have to know in your mind going into that you're going to have this exception. So that's going to be that one. Here we go. We got another question that came in. Cromarty, do you have any tips for aligning a measurement on a bowed wafer?
Higher incident angle probably is what I
Make
would
it
recommend.
not bowed.
Yeah, right.
That's a good one.
Yeah.
Yeah.
I mean, so for samples that I've had issues with like that, basically, right? I had better luck picking a higher 2 theta angle as long as I still get reflection from that to align the specular reflection on the detector.
Yeah, another tip would be if it's bowed in only one direction, you can try to turn it so you get the minimum amount of bow between the tube and the detector. Another tip, smallest possible beam size.
Yep.
And there, what can really help you, not only laterally, right? So you can use a height limiting slit, reduce the size that way. But then also what you might want to use is what's called a knife edge. So a knife edge sits very close to the sample surface, and that's going to limit the amount of the sample that's being measured. You do have to be thoughtful, because if that knife edge is very close, then at higher angles it'll start to cut some signal.
Right.
So generally what we might do is measure the first range of 0 to 1 degrees with the knife edge in. After 1 degrees, raise the knife edge, complete the scan. But then we can limit the size of the beam, the footprint of the beam, and that's going to help you a lot with the bowed wafer.
Yep. Yeah, good points. Good question.
Yeah. But the other thing is, maybe you can use a wafer chuck to suck it down a little bit. Hopefully you don't crack the film. But
right.
That's a possibility. Now a question from Jidong. Is this setup also good for GSACs?
Are you referring to like the experimental setup?
I think so.
Yeah? Probably would want an Eiger for that, because you're going to start to, because with GSACs, I believe you're sampling in equatorial and axial directions. You're having a more narrowly defined beam, right? So.
Yeah, so SACs in general, small angle X-ray scattering. What we're generally looking at there is density differential. A classic sample for SACs might be particles in a liquid. And we look at the scattering differential between the beam that's going through the particles and the beam that's going through the matrix material, and that gives you some sort of a pattern. And it's actually very similar to what we're seeing in XRR, very large fringing. And what we're generally looking there is also in the same length scale, a few nanometers. Now GSACs, what that adds to it is, we're not just doing the classic transmission SACs measurement, rather we're going to take the beam, bounce it off of the sample surface. So yes, in that case, we are going to be coming in at a very low angle. In fact, the ideal angle for GSACs is right at that critical edge, because that's when the beam comes in and then tunnels along the surface, or is redirected along the surface of the sample and catching a bunch of information. Now you can do this in a one-dimensional method, so you can just park at that critical edge and then do a scan of your detector, and you're going to get something that kind of looks like these XRR curves, but it's coming from the particulate that's on the surface. If you want to take it up a notch, you could use a point beam. Something like a microfocus that's going to give you a really nice point beam on the sample surface. Use a 2D detector, like you mentioned, like the Eiger, and that's going to give you a nice two-dimensional view. And there we can start to see features like lines or dots that indicate the amount of ordering that's happening, whether that's lateral ordering, vertical ordering, things like this with those nanoparticle arrays. So the answer is yes, very, very similar setup, very low angle. We want to be thoughtful about air scatter, things like that. A little bit different in how we're going to collect the data. But yes, very, very, very similar setup. So one other question that had come in is, can this be automated? I think they meant the analysis.
Yeah.
And that comes from Steve.
Yeah, great question, Steve. So there's a whole workflow section in the software. The manual actually does a very good job of going over tutorials on how to set that up and things like that. So yeah, I mean, as you know, you've seen some of the stuff that we've done today, which is pulling in pre-saved sample information, stuff that you can add to the database to help move that automation along, and then workflows to kind of pull it all together. Yeah, so the workflow, that's going to be something very visual. You can put in these blocks of the different things. You can record them, in fact, and it's going to give you a simple walkthrough of doing the analysis. Another thing to note, though, in this new version, what we just released, is that we really help to make more stable the automation. So the automation in terms of you can have your sample be measured and then automatically do the refinements. So that's also in the background. So with that, if you do have any other questions, again, you can always send them to live.events@brooker.com. But until next time, I'd like to thank you for joining us, and thank you, Jonathan. Thanks for having me on, John.
And until next time, keep your signal high and your background low.